Satu, dua, tiga. Hello everyone, we're from Group 8 and today we're going to present our results from study case 5 that is titled Structural Health Monitoring for Bridges. But first, let us introduce ourselves. My name is Nadia.
My name is Nelsa.
My name is Nadia.
And my name is Afe.
For table of content, we're gonna discuss about the study case first, and the second one is problem understanding, and then pattern recognition, and then data representation and abstraction, and then flowchart. Then the last one is pseudocode. For the study case, we break down into several points that is called decompositions. For the first is data collection problems, where we have to decide which effective way to place and distribute the sensor, and then insert the data transmission continues without any interruption, and then for accurate analysis, reduce the noise in raw sensor data. We have to decide which way is the effective one. And the second one is data processing and analysis problem. We filter out the irrelevant and the noisy data, and then we detect the anomalies in several factors, and then we search for the extreme values in large data sets, and the last one is handle the missing data points in a real time. The third one is structural health assessment problems. We have to determine the detected anomalies that indicates structural failures, and then for prediction we compare the real-time data, and then we classify the structural issues, and then we estimate the remaining lifespan. The fourth point is maintenance prioritization problems. Based on its risk, we have to rank the maintenance tasks, and then we have to scheduling the repairs, and then we have to, based on degradation, we predict the future maintenance, and then we ensure the repairs to minimize the long-term cost. The last point is scalability and cost-effectiveness problems. We have to design a system that can scale the multiple bridges, and then we have to optimize the data storage and also the process for the efficiency. And the last one is we have to integrate the existing infrastructure for seamless deployment.
The problem understanding. Bridges undergo continuous stress and load variations due to physical, environmental factors, and material fatigue. Without early detection, structural issues can lead to failures or even disaster. This study focused on a sensor-based monitoring system to detect first is excessive vibration and overloading. Our goal is to develop an automated system that monitors real-time sensor data, compares readings with predefined safety system limits, alerts engineers when dangerous conditions are detected, and last is helps in decision making for maintenance and repairs. The pattern recording. There's three conditions. First is normal conditions. The vibration is less than 2 millimeters. Structure is stable. And for the load is less than 30 tons per section with safe weight limits. And for the warning signs conditions, the vibration is more than 2 millimeter. And for the load is more than 30 tons. And last is the critical failure conditions. The vibration is more than 4 millimeter, is a high risk of crack, and for the load is more than 35 tons. Pattern use case is if the vibration is increased over time, the bridge may be weakened, and if peak loads exceeds 30 tons regularly, heavy vehicles may be overloading the structure.
And here's our data representation and abstraction. For data collection and monitoring, sensors are strategically placed on the bridge, like on the pillars, joints deck, and data on vibration and load is collected. And then for threshold-based alert system, we have 3 levels: safe levels, warning levels, and critical failure. And then for the decision-making process, if a sensor detects dangerous levels, an alert is triggered, and then anomaly is logged in the database for analysis. And then for the engineers decide routine maintenance if within warning levels, and then immediate inspection if in the critical range. Oh, so this is our flowchart for the step-by-step explanation. First, start the process. The system begins by initializing sensor at the critical points and then reading the sensor data. The sensors collect data related to vibration and load pressure. And then we check for the initial anomalies. Here, the system check if the vibration exceeds 2 millimeter or load pressure is above 30 tones. If no, the system continues monitoring. And then if yes, it triggers the alert to the engineers and logs the anomaly in the database. Then assessing severity of anomaly. After logging to anomaly, the system checks for more severe condition. Vibration exceeding to 4 millimeter or load pressure above 35 tons. If no, the system returns to continue monitoring, and then if yes, it requests an immediate inspection for further investigation. Then we're here to the end of the process.
Now I'll be explaining about our pseudocode. So after starting our pseudocode, we set up sensors at various bridge locations to monitor vibration and load. We excluded the temperature because we thought that it might not be that effective. So then we threshold the values for vibration and load. The safe limit at max vibration and max load, it is 2 millimeters and 30 tons. Then the dangerous level is the critical vibration and critical load at 4 millimeters and 35 tons. And then we do the while loop. It is for continuous monitoring. As long as the monitoring is active, the system will read the data. And then after that, we focus on highest risk by greedy approach. We find the highest vibration and highest load. Then after that, we do a decision making for immediate or routine action by severity check. If the vibration exceeds 4 millimeters or load exceeds from 35 tons, the situation is critical. So it will request an immediate inspection to prevent the bridge to fall down. And then last but not least, we ensure that there are no risks missing from the sensors individually. And that is all for our presentation this time. Thank you and goodbye.